Okay, so today we're going to talk about energy and motion for our Year 10 physics unit here. First, we're going to start off by talking about what work is. So work is, we've heard that term before, just people go to work whenever, in a normal daily idea of using it, but it has a use or understanding in physics which we mightn't have come across. So it says here, whenever a force moves or rearranges something, work is done. This is known as mechanical energy. Okay, the larger the force acting, the greater the work is done. So imagine someone pushing an object or a force that's making an object move. The longer the distance over which the force acts, the greater the work is done. If a force is applied or acts, but nothing moves, then no work has been done. So if you're pushing against a tree, for example, tree doesn't move, it's a big tree, then you're not doing any work with that force. Okay. So work is a measure of the amount of energy used in moving an object. Now I talked a bit about some of these ideas before. Work and energy, basically they're the same thing. They're measured in the same quantity. And it says here, as work and energy are scalar quantities, no direction is needed. Remember, they're scalars as opposed to vectors. Vectors were things like velocity and acceleration and force, which you needed to specify a direction as well as how much it is, what we call a magnitude. Okay, so work is measured in joules after a famous physicist and can be calculated by the simple equation work done equals force applied times the distance moved in the direction of the force. So we've got to notice that it's the distance moved that's in the same direction as the force. So if there was a force applying, but the direction that you moved was actually at right angles to that force, there'd be no work. We'll talk a bit about that later. Anyway, we've got this formula, work, W equals F times D. And we've got a little triangle down here, a little equation triangle like we use with velocity. And we're going to try and work out where we would put our W, F and D to help us, just like we did in the case of velocity. So remembering that we have to have a divide sign there, and down at the bottom here we have a multiplying sign. So I just want you to take a minute, just turn the YouTube video off and just have a think about where you would put the W, the F and the D to make sense in this triangle. Okay, so hopefully you've had a little bit of a think about this. So what we would do for this triangle, it would be W equals F down here times D. Okay, so that's how we would use that triangle. If we wanted to know the force and we knew how much the work was done and how much distance that object had moved, we cover up F and we see that F equals W divided by D. There's the same rules as we used to operate this triangle as we did before. Just with this time, it's with just different variables. Okay, going to go now to power, and here's a very common term that we use. People always talk about the power, how powerful someone is, or the power gets cut off. Mostly we talk about it in terms of electrical energy. So anyway, our actual physics definition is power is the rate that work is done, or how fast energy is being used. So power is measured in watts, after another physicist there, or it could be measured in joules per second. That's how much energy is being used per second. And we can develop a little algebra triangle, equation triangle for this one. And this time it's power equals work divided by time. So I just want you to remember, yeah, we've got a divide there and a times down here. So just turn the YouTube clip off for a tick and have a think where you would put the P, the W and the T. Okay, so hopefully you've had a little bit of think about that. So here we'd have to put the P down here for power, W up here, and the T for time taken would be here. So therefore we can use this. If you don't like your algebra very much, you can use this to work out little equations about power, work, and time. For example, if we knew how much power we were using and how much work we'd done, we wanted to know how much time that it had actually taken to do that amount of that work at that power rating, we'd cover up T, and we say T equals W divided by P. W and P are the only things left. It's W divided because that divide sign is up there, and we cross there. Okay, let's just move on now. And we've got a worked example here. And so we got Tom pulls Sue on a sled for 10 seconds with a force of 120 newtons. Remember, force is measured in newtons. It's over a distance of 3 meters. So if someone's just pulling a sled, takes them 10 seconds to pull this sled 3 meters with a force of 120 newtons. And we want to calculate the work Tom has done on the sled. So he's doing it on the sled because Tom is the one pulling, and the sled is the thing that's being acted on. And the second bit, Tom's power in pulling the sled. So first of all, we've got force equals 120 newtons, distance equals 3 meters, and there's our equation just there. Work equals force times distance, and that equals 120 by 3, which equals 360 joules. Okay, so that's our answer there. The work done, the power in pulling the sled, well, we know power equals the work done divided by the time it took to accomplish this task. So the work done was 360 joules, that's just from the first part A, divided by 10 because it took 10 seconds. So power equals work divided by time, 360 divided by 10, that equals 36 watts, or 36 joules per second. So what we're saying is that Tom was having to burn up 36 joules of energy every second to accomplish that, or 36 joules per second was being exerted on the sled. Okay, hopefully that's sort of you got that one worked out. So here's your turn. I want you to do a simple calculation here. A child of weight 250 newtons climbs 1.5 meters up a rope ladder in 5 seconds. Calculate the work done and the power of the climb. So I'd like you to just turn off the YouTube clip here, have a little think, do those, have a go at those questions, and we'll come back and do the answers together. Okay, hopefully you've had a bit of a think about that one. So the first one, we're going to use our equation, work equals force times distance moved. And this is going to equal our 250 newtons because that's how much she weighed. So she has to combat that force of weight. She has to put 250 newtons of force to move up. And times by 1.5, because that's how far it was, she had to move up, and that's 375 joules. So that's how much work, that's how much energy that this child has to put in to, if they weigh 250 newtons, to climb 1.5 meters up a rope ladder. Now the power of the climb is the rate at which work is done, so it's the work divided by the time taken to do this task. So this is our 375 joules divided by 5, and that equals 75 watts, or 75 joules per second. So that means that this child has to consume, or has to exert, has to be able to, it needs to put out 75 joules per second of energy to accomplish this task. Okay, we'll just leave it there now for that one, and we'll come back and continue on with our talk here about energy and work.